those cuprate reagents we just saw were really nice, versatile ways to make some carbon-carbon bonds that we might have a hard time making in other ways. The downsides to those cuprate reagents are that, A, I have to use a lot of copper, right? So I'm asking to use stoichiometric amounts of metal, which is to say like a full mole of metal per mole reagent. And also, they're a little bit basic still, and they're kind of a little tricky to work with. It would be better if we could do this with metal catalysis, which is to say a metal catalyst that turns it over instead of a full equivalent of metal. And it turns out that modern organic chemistry relies really, really heavily on palladium catalysts to make carbon-carbon bonds. You really cannot pick up an organic synthesis paper over the last 20 years where they don't rely on this reaction or one very much like it somewhere in that paper. Okay? And so, again, to bring you a little bit into at least the 21st century of organic chemistry, we need to cover the Suzuki reaction. Your book covers 3 organometallic reactions in this part of the textbook, the Suzuki, the Heck, and the Grubbs alkene metathesis. We're not going to talk about the Heck reaction in this course. We might talk about metathesis at the very end of the course, but we'll talk about the Suzuki in some detail, and then we'll talk about one reaction that isn't in your textbook called the Sonogashira reaction, which is very similar to this. Okay, what's the Suzuki good for? So the Suzuki reaction takes some sp2 halide, so something with a bromine, chlorine, or iodine, some leaving group on it. This is often a benzene ring, but it does not have to be benzene. It can be any double bond there. And it takes some boronic ester. So again, we don't see boron a lot, but here is a species with one bonded boron over here and 2 boron-oxygen bonds. I said earlier that organoboranes aren't really stable, but these boronic acids are a fair bit more stable than your typical alkyl boron thing. So this is something that I can buy. They're pretty cheap. Again, this can be just a double bond or it can be a benzene ring. Phenylboronic acid is like $3 a gram, so these are relatively cheap to get to. And in a minute, we'll talk about how we might synthesize something like this from an alkyne. Your textbook says that you don't need to just use sp2. You could have a single bond here and there. That's technically true, but those reactions are not nearly as useful and as reliable as the Suzuki that goes sp2 to sp2. So when I think of the Suzuki reaction, I'm really more focused on making bonds between 2 sp2 carbons. One of the reasons I'm focused on that is because I don't have a better way to do that in Chemistry 252. Right? We've learned a lot of new reactions even in our first week of the course, but really don't know a better way to make this cool sp2-sp2 bond. So very, very useful, and I can show you a bunch of drug and drug candidates that people have tried to make or have made with the Suzuki reaction and reactions like it later on. You might be wondering how I get these boron compounds. Sometimes I can buy them, but they're actually easy to make, especially if I want a trans double bond like that. If I only take an alkyne and react it with what we call catechol-borane, really there's lots of boranes that will do this. But if you remember how boron attacks pi bonds like this, we learned this reaction earlier. We sort of have this concerted reaction where the boron and the hydrogen end up adding to the same face of the pi bond. And here this boron group is big enough and bulky enough where I'm not going to add a second one. It'll only add one. So this is a great way if I want a trans double bond especially. If I want a cis double bond, I'll have to be creative and And frankly, we don't know any good ways to do that. But in this case, I can go from an alkyne to this alkenyl boronic ester. Just to use this in an example of a Suzuki reaction, I could treat this with this ring. It's 5, remember, it's not exactly benzene, but I still have this sp2 carbon bound to bromine. Give it some palladium catalysis, or palladium catalyst. Give it some hydroxide base. Suzuki reaction, new bond, right here, works. Okay, I'm going to go through the catalytic cycle for the Suzuki reaction. I'm going to go through the full mechanism. You do not need to memorize this mechanism, but I want you to roughly understand what's at play here. Okay, so here is a common Suzuki reaction as we might see it. So I've got some sp2 carbon bound to oxygen, or bound to boron with 2 oxygens on it. This is made from something called catechol borane, but what's over here really isn't so important. It's not going to be part of the product. And over here I have some sp2 halide. It's often on a benzene ring, but not always, doesn't need to be. I'm going to use some palladium catalyst. So we very often see something called palladium tetrakis. So it's tetrakis triphenylphosphine. So I've got 4 phosphorus atoms surrounding the palladium center. And I've got 3 big benzene rings around each of those 4 phosphoruses. So I've got like 12 benzene rings kind of all surrounding this palladium center. And I want to do that to protect my metal atom in my catalyst and to keep it soluble. What I don't want is a bunch of palladium atoms glomming on top of each other and deciding to be a rock, because metal atoms like to be, a block of metal. Anyways, I'm going to have some catalytic amount of palladium. This is very expensive, but I might only need a few percent of it, a few mole percent. And I'm going to also add some kind of oxygen base. So it could be sodium hydroxide. This is sodium methoxide, some kind of alkoxy base. My product is going to end up, again, having this new sp2-sp2 bond. How does it work? Okay. We'll start here. My palladium starts off with these 4 ligands. Again, our ligands here are these phosphorus atoms. And this is what you'll learn in Chemistry 320 with Graham Sazuma. But these ligands can kind of go off and on reversibly pretty easily. So we sort of wait until 2 of the ligands have popped off. What that does is it gives me some open area on the metal for a reaction to happen. So now my palladium is going to oxidatively insert. This is that oxidative insertion we've seen a few times now. It's going to oxidatively insert into this carbon-bromine bond. So now I'll get something like this. Again, it's an oxidative insertion because technically we would call this palladium 0 and this palladium 2 if we had had Chemistry 320 already, which we have not. So now this complex is actually going to swap out this bromine for either hydroxide or whatever base we give it down here. What does that do? Well, it makes it more reactive, especially for what's coming next. So now I'm going to swap out this oxygen for this alkyl group, right? So I'm going to break this CB bond and make a new C palladium bond. And I'm going to break this palladium oxygen bond and get a new boron oxygen bond. So this is another form of transmetallation. I'm swapping partners. And the driving force for this is that boron-oxygen bonds are really, really strong. This is essentially borax. It's a really, really electronegative oxygen, electropositive boron. So the boron-oxygen bond is very, very strong. Okay, so that's what's driving this reaction. Once I have a palladium with 2 palladium carbon bonds, it's going to do a reductive elimination. So just like it wiggled into this CBr bond, it's going to wiggle back out, get me back my palladium with 2 ligands on it, and spit out my product. All right? And you can crank this as much as you can. Right? So that's a beautiful catalytic cycle. I don't want to use a full mole of palladium every time I want to do this reaction. Palladium is really expensive, and I need it for my catalytic converter in my car. And so this helps us get away with, yes, I have to use an expensive metal, but I only need a little bit of it to turn the crank here. And not to belabor the point, but if you look at a drug company's warehouse of potential drugs and molecules that they test against the targets that they find, there might be 3 million drug candidates in there, but a lot of the drug candidates are going to have some sp2 bond like this. They're going to have a benzene ring attached to other benzene ring or something like that. And most of those ring-to-ring bonds were made with this reaction, or made with the Suzuki reaction. When will I use this? I will use this every time I see something that has a carbon-carbon bond between 2 sp2 carbons. My brain is going to say, okay, I can make that bond with a Suzuki coupling.